So we're going to discuss question 4 of the counting tutorial. Now question 4 asks about how many ways are there to sit 6 people around a circular table where two sittings are considered the same when everyone has the same 2 neighbors without regard to whether they are right or left neighbors. Okay, so in order to appreciate how circular permutation is different from line permutation, we are first going to consider line permutation, and then we're going to try to sit them around a circular table. So, and because 6 is a big number, if you look at all the possible permutations, you're going to start with a smaller number. And let's suppose that we're going to start with 3. Okay, we're going to see the problem from the point of view of just 3 people. Now, if there are 3 people, then we can ask the 3 people to essentially first form a line, right? So we ask them to line up, and then based on who is first, who is second, who is third, then we can determine the chair for them. So let's imagine for the moment that we are going to have a circular table. Okay, and let's say this is a circular table. And let's say we're going to number the table 1, 2, 3. Now, what we're going to do is to ask each person to first line up, and then we're going to ask the person who is first in line to sit at number 1, and then the second person to sit at number 2, the third person to sit at number 3. So one possible permutation is going to be A, B, C. Now, since ABC is one permutation and A is first in line, so we're going to ask A to sit here. And then we're going to go clockwise. B will be in the second one and C will be in the third one. Now, this is one possible permutation. And because we have 3 people, there are different permutations that are also possible. Now, we're going to enumerate all of them. Okay, so another possibility is that we're going to have, instead of ABC, so we're going to have CAB, as well as BCA, as well as BCA, CBA, and BAC, and ACB. Alright, and for each of them, we can then draw the corresponding table. So in this case, in this table, because C is first in line, we're going to put C in position 1, and then followed by B, followed by A. In this table, we have C in position 1, followed by A, followed by B. And in this position, we have B, A, C, A, C, B, and B, C, A. So because we begin with 6 different line permutations, we end up with 6 circular permutations, 6 circular tables with different sitting arrangements. Now, we're going to pay a little bit closer attention, and here we realize that some of these arrangements are essentially the same. Now, let's first consider this one and this one. And we realize here that in this case, A has 2 neighbors, which is B on this side and C on this side. And we consider this table, the difference essentially is just to rotate this table by 1 clockwise, where A is going to move to B position, B is going to move to C position, C is going to move to A position. So then we get this essentially this table. So but if you look at the neighbors they have, A still has B here and C here. In this case, A still has B here and C here. And C still has B on this side and A on this side. C still has B on this side and A on this side. And B still has A on this side and C on this side. So B still has A on this side and C on this side. Essentially, the 2 neighbors are all the same. And we can follow the same reasoning and realize that this table has the same arrangement too. because essentially what we are doing now is that we have rotated the table one more time by one position to the right, and in this case then B is going to go to where C is going to go to where A is, and A is going to go to where B is. So then we get this table instead, but in terms of the sitting arrangement, they are still all the same. So instead of 3 different ones, they're essentially still the same arrangement. Now let's consider this one and this one. So here, CAB is going clockwise. In this case, we have CAB going in anti-clockwise. But in this case, all the 2 neighbors are still the same. So if you consider C has A on this left side and B on the right side. In this case, C has A on the right side and B on the left side. So they are essentially mirror images in terms of the clockwise and anti-clockwise. But we don't actually care about this, because we say that as long as they have the same 2 neighbors, without regard to whether they are on the right or the left. So essentially each of these are mirror images. So this is CAB going clockwise, this is CAB going anti-clockwise. CAB going clockwise, CAB going anti-clockwise, but essentially all the neighbors are the same. Now in that case, it means that all these 6 tables are essentially the same table. And if you think about this, it actually makes sense, because out of 3 people, you always have the same 2 neighbors regardless of where you sit. So how many possible circular arrangements can we have for 3 people? There is only 1. Now how do we get this one? So we first put them in a line, which is going to be 3 people in a line, so it's 3 factorial. Now this is if we put them in a line. But in a circle, we can rotate the circle 3 times and essentially still get the same circle. And finally, because the requirement is that we don't care whether they are right or left neighbors, so for every table that is going clockwise, we can have another table that's going anti-clockwise, but essentially still the same arrangement. So in that case, we need to divide by 2. So then this is going to be equal to 1. So in the general case, for n people, then we can put n of them into a line in n factorial ways, and realize that every circle can be rotated n times without changing the relative position among the people. And if you don't care about whether they are on the left or on the right, and it's still the same neighbors, then we need to divide by 2. So the answer to 6 people would just simply be 6 factorial divided by 6 times 2.